Now I want to talk about compositions of multiple linear transformations. So we've already talked about a composition where maybe you move from one subspace to another. So maybe we say that this is the set A, this is the set B, and we have some transformation that moves us from vectors in A to vectors in B. Well, now we want to know what happens if we also want to take that result that we got in B and transform it over into a space C. So we'll call this space C. And after we have transformed the vector from A to B, we want to take that result and move it from B over into C. In other words, we could call this the transformation S and this the transformation T. And so if we started with some vector A that's in A and it moves over to B, the vector we would get here would be S of A. In other words, what happens to A when we transform it with the transformation S. But then if we want to take that result, S of A, and transform it with T into C, that means we're going to end up with T of S of A as a vector that's in this space C. And we want to say here too that A is in Rn space, B is in Rm space, and C is in Rp space. N, M, and P don't necessarily have to be equal. We could be transforming across spaces, or they could all be equal. We could be transforming all within one space. But the idea here is that the transformation S moves vectors from the space A to the space B, and then the transformation takes those results and moves them from B over to C. If we want to express those transformations together as one sort of consolidated, combined transformation, we call that the composition, and that's the composition of T with S. It's really important here to realize that the order of these transformations matters. So when you look at a diagram like this and when you think about it, you might think we're doing the transformation S first and then T. And so when you write the composition of the two transformations, you may be tempted to write S of T of a vector A, or we can also write it this way, S circle T. This means the composition. This little circle means the composition. So you might be thinking that this is the appropriate composition because we start with S and then we do T, and so you have S and then T. But these are actually both wrong. And that's because you can think about these as being nested. When we apply S to a vector A, we get this S of A. When we then apply T, we take the transformation of this whole thing. So you now have T of S of A. So the correct way to write the transformation of S and then T is like this. We either say the transformation S and then the transformation of that by T, or we say T circle S of the vector A. So this order kind of feels backwards because you think S then T, but when you write it out, it's actually T then S. This is the correct way to express using the transformation S first and then T. And so when we have a composition of linear transformations, it's important to realize that the composition is closed under addition and closed under scalar multiplication, and that because S and T are both linear transformations, we can write them as matrix vector products. So if we, for instance, say that we'll say the transformation S of a vector A, we'll write that as, let's just say, the matrix vector product A times the vector A. So we just have some matrix A here. And then let's say that we write T, and we'll just say here that if we rename this vector here, S of A, let's say we rename it as B. T takes vectors B, and we can express that transformation as the matrix vector product B times the vector B. And in this case, because we're saying that A is defined in Rn space, B is defined in Rm space, and C is defined in Rp space, by definition, the matrix A has to be an M by N matrix, and matrix B has to be a P by M matrix. Now here's sort of the unlock when it comes to compositions of linear transformations. Instead of doing these one at a time, we can combine them and write them as one composition. And the way that we do that is we say that the composition of t with s, we'll say of the vector A that we start with over here in A, we can write that as, we'll do it with parentheses, this first expression, instead of the circle here. So we'll say t of s of A. And then we know that S of A can be written as the matrix vector product, the matrix capital A, and the vector A. So we can rewrite this as T of matrix A vector A. But because we know that T can also be written as this matrix vector product with the matrix B, we can actually rewrite this as B times A times the vector A. And B and A are both matrices. And so when we multiply those matrices together, they'll combine into one matrix. And so if we say that BA is actually equal to C, we'll use a capital C here, then this is just going to be C times the vector A. So this composition of the two transformations, if I take the transformation that transforms the vector A into a vector in B, and then takes that and transforms it into a vector in C, to get that resulting vector, all I have to do is find this transformation matrix C and multiply it by the vector A that I want to start with. So to give an example, if we say that the transformation S of a vector A is given by, and we'll just take a matrix here, 2, 0, -1, 4 times the vector A, and we say that the transformation T of some vector B, which is what we end up with here, S of A, we just rename it B, but that takes vectors that are in B and transforms them, we'll say -1 and -2, 3, and 0. So we're expressing both transformations as matrix vector products. These tell us what the transformations do. And let's say we're interested in transforming the vector A is 3, 2. Then truly all we have to do is take this matrix here and multiply it by this matrix. So we'll say the transformation T of S of some vector A that was in A is going to be equal to, we always have to take our matrix from T first. We're kind of working backwards. So we take -1, -2, 3, and 0, and we multiply that by our first matrix, 2, 0, -1, 4. And the result there for this matrix, if we take dot products, will be -1 times 2 gives us a -2, and -2 times a -1 is a +2. I add those together and I get 0. -1 times a 0 is 0. -2 and a 4 is a -8. 3 times 2 is 6. 0 and -1 is 0. 6 and 0 is 6. 3 and 0 is 0. 0 and 4 is 0. So I get 0 here. So this is my transformation matrix C, the one that we wanted here. And now to transform the vector A by that matrix, I just say C times the vector A. I'll use 0, -8, 6, and 0, and multiply that by 3, 2. And so my result then will be 0 times 3 is 0, -8 and 2 is -16, 0 and -16 is a -16, and then 6 and 3 is 18, 0 and 2 is 0, 18 and 0 is 18. So what this tells me then is that if I start with a vector 3, 2, so I start with a vector 3, 2 that's inside A, it undergoes the transformation by S, and then it undergoes the transformation by T. So we don't even know the vector we get to just after the transformation S. We don't stop halfway. We're going all the way to C over here because we were able to combine the two transformations. So we start with 3, 2, after the transformation by S to get us into B, and then after the transformation by T to get us into C. The resulting vector here is -16, 18. So we end up with here -16, 18. And so using a composition of transformations, we were able to go directly from A all the way to C and find the transformed vector without having to do each transformation one at a time, but instead combining them into one transformation that was the composition of the two separate transformations.